So assuming that you would have done this, so the next set of elements are in finite elements is the plate elements. So then I will talk about linear finite element formulation of plate elements. So we will discuss two types of plate elements. Plate elements based on classical Kirchhoff plate theory and plate elements based on Mendelian first order shear deformation theory. So this is what will be discussed in this linear finite element formulation of plate elements. So then you have this. Then I will introduce this geometric nonlinearities. So introduction to geometric and material nonlinearities. So essentially the geometric nonlinearity we are going to consider is through the strain displacement relations. So the nonlinear terms in the strain displacement relations will be the source of geometric nonlinearity, and material nonlinearity could be elastic. Material behavior is nonlinear elastic. So as an example, we will consider hyperelastic materials and also the material with elastoplasticity. So that is also an example of material nonlinearity. So under this material nonlinearity, we would do two things: hyperelastic materials, which are nonlinear elastic, and elastoplastic materials, which are also materially nonlinear problems. So in the area of geometric nonlinearity, I will give you the basic background on Lagrangian and Eulerian description of motion. Then for large finite deformation, the strain and stress measures. So in strain measures, I will talk about Green Lagrange or Green strain tensor, Almancy-Hamel or Eulerian strain tensor. Then Cauchy stress tensor, first Euler-Kirchhoff stress tensor, second Euler-Kirchhoff stress tensor. And so after talking about these stress and strain measures for finite deformation, we will talk about what are the energetically conjugate stresses and strains. So for example, the Cauchy stress tensor is energetically conjugate to the basically the essentially the gradient of displacements. And then the first Euler-Kirchhoff stress tensor is energetically conjugate to deformation gradient. The second Euler-Kirchhoff stress tensor is energetically conjugate to Green Lagrange or Green strain tensor. So these are the things I will be talking about on this. Then I already said hyperelasticity, and then I will also talk about rate dependent materials. So linear viscoelasticity is one such example of rate dependent materials. So I will talk about linear viscoelasticity. So I will talk about constitutive relation and finite element formulation of linear viscoelastic materials. Then we will take as an example different examples on geometric nonlinearity. So nonlinear finite element formulation of truss elements, beam elements, plate and cell elements. And then we will also talk about the for nonlinear problems different solution techniques. So Newton-Raphson method, because the problem is nonlinear, you have to use iterative technique. So Newton-Raphson method. Then in the equilibrium problems, nonlinear problems, you have you vary say a load parameter, and then you want to see how the the deformation continues, the equilibrium path. So path continuation techniques I will talk about. So arc length continuation is one such example of path continuation techniques. And I will also talk about dynamics problems, and for nonlinear dynamics problem, if you want to extract the steady state solution, how can you use the shooting technique? So for nonlinear dynamics problems where you are interested in steady state response, so there is a technique called shooting technique. So directly we can extract the steady state response. Otherwise, if you're doing time integration, you have to integrate it for a sufficiently large time duration to reach to the steady state solution, and that is very time consuming, whereas shooting technique gives this steady state solution much faster. So I will talk about that. And the last topic I will talk about is the finite element formulation of now you basically deal with problems involving contact, so contacts between two or more bodies. So you have to model this contact in finite element formulation. So I will be talking about that, how to formulate a contact problem. So contact is also a kind of nonlinearity, and that we will be talking about. Then you have this references. So no, you can find some of the content I will be talking about is you can find in the nonlinear finite element analysis by J.N. Reddy. Also, weak form you can find actually in the linear finite, so finite element analysis by J.N. Reddy. So weak form actually you can study from that. And then the nonlinear problems from nonlinear finite element analysis of J.N. Reddy. Then some topics from finite element procedures from K.J. Bathe, and many of the topics I will be taking from advanced topics in finite element analysis of structures by A.M. Asghar Bhatti. So this reference. So many of the topics I will be covering from this book. So this is about the course content and the reference books. And now coming to the evaluation. So evaluation, we will have one minor test which will be having weightage of 30%. And then we will have major test which will be having weightage of 50%. And I will be giving you some assignments and I might conduct some quizzes, so those will have a weightage of 20%. So that makes it total 100%. Assignments and quizzes, some of these would be actually programming assignments which you'll have to do in MATLAB. So you should also familiarize yourself with MATLAB if you have not done already. So you should learn MATLAB. So you will be doing these programming assignments in MATLAB. So that's one, and no, you can write to me if you have any doubts and question. You can ask during the class when I'm discussing. You can stop me in between, and you can ask your doubts. You can ask doubts at the beginning also of the lecture. You can ask doubts at the end of the lecture, or you can write me an email. My email ID is bppatel@am.itd.ac.in. So yeah, so this is about the course. If you have any questions on this, you can ask.
Hello.
Yes. Yeah.
Yeah. Good morning, sir. I have one question. So,
Yeah.
are we going to discuss about wave propagation problem? So, I saw in the course structure, it was written wave propagation also.
Yeah. So when I talk about dynamics problem, so in dynamics problem, I will talk about the time integration techniques. And in that discussion I will be talking about wave propagation. You use basically the same elements, dynamic problem. So as far as the finite element formulation of wave propagation problems is concerned, so the finite element formulation is same as a dynamics problem. So I will be talking about dynamics problem, and then when you integrate the equations of motion, so for wave propagation problem, we have to choose delta t and length of the element appropriately. So that is
Okay.
what is specific to wave propagation problem. So yes, I will be talking about that.
Okay. Thank you, sir.
Anybody else has any clarification doubts on the course content? I have discussed evaluation scheme, references, etc. Okay, so yeah, then let me start with the weak form. So I close this course content, and I will open the this Windows journal file. So is the screen visible? Hello, is my screen Windows
Yes, sir.
Journal
Yes,
visible?
sir.
Yes, sir. It is visible.
Yes, sir, it is
Okay,
visible.
okay, okay. So yeah, so that's the first topic I'm going to start, that is weak form. So essentially, when we try to find out the approximate analytical solutions of differential equations. So we write the weighted residual statement, and to arrive at the weighted residual statement, let's say we have a differential equation. So in the differential equation, in place of the unknown variable, we substitute an approximate solution. So approximate solution will not satisfy the differential equation, so there would be residual. We multiply that by a weight function and write what is known as weighted residual statement. So if we use the weighted residual statement as it is, the differentiability requirement of approximate solution is as per the differential equation, which is higher. So to reduce the differentiability requirement of approximate solution, we do the integration by parts and transfer some of the derivatives from the unknown variable to weight function. So whatever resulting expression we get, we call it as actually weak form. So let me demonstrate this through an example. So let us say I will take a simple example, that you have a bar and this is the x coordinate, and along the x direction we have the displacement u, and this bar is subjected to a distributed force per unit length along its length. So let us say that is q, and length of this rod is l. So boundary condition in this case are u equal to 0 at x equal to 0, and this end is a free end. So you have ea into du by dx equal to 0. That is at x is equal to l, ea into du by dx equal to 0. So for this, no, you would have done differential equation. So if you look at the governing differential equation for this problem, governing differential equation. Yeah, so the governing differential equation for this problem is d by dx of, so basically you take a small differential element and draw its free body diagram and write the equilibrium equation. I am considering equilibrium problem. So it's a static problem. D by dx of EA into du by dx plus q equal to 0. This is the governing differential equation for this, where no your E is Young's modulus, A is cross sectional area, and Q is load per unit length. I have already shown in the figure over here. So this is the differential equation. Now we want to find out the approximate analytical solution for this differential equation. So in place of this variable, unknown variable u, we substitute an approximate solution. And when we substitute that approximate solution, so the left hand side will not be actually 0. So whatever we get, we call that as residual. So then we write what is known as weighted residual statement. Weighted residual statement. So now in this weighted residual statement, what we do is as I said, when we substitute the approximate solution, although I'm going to use the same notation for exact solution for u and approximate solution. So in the when we write it in the weighted residual statement, so it is understood that u is an approximate solution, and when we write the strong form, that is this differential equation, then u is a basically exact solution of the differential equation. So the weighted residual statement is integration over the domain. So because this is a one-dimensional problem, so the integration is integration 0 to L, and then we have residual, which is d by dx of Ea into du by dx plus q. So as I said, when we substitute the approximate solution, so if u was an exact solution of the problem, then this term would be actually equal to 0. But when we substitute an approximate solution, this u is not 0. Of course, we have transferred all the terms, we have all the terms on the left hand side, and then whatever we get, that we are calling it as residual. So this is the residual. Then we multiply by a weight function, which is a known function, and that's a function of x. So I'm calling it as w, and then integrate it over 0 to L, and then equate it to 0. So when we write this, we call it as weighted residual statement. So here this w is a weight function. So no, it is one thing is that it is known, and it is referred to as weight function, and it is a function of no, obviously x. So this is a no, we call this as weighted residual statement. So the important steps you will notice that we have a differential equation. We transfer all the terms of the differential equation to the left hand side, and then whatever we have, because we are substituting an approximate solution in that, so we whatever we get is not going to be 0, so we call that as residual multiplied by the weight function w, and then integrate it over the entire domain, and whatever we get, the resulting expression is known as weighted residual statement, and this term is actually residual. So now if you are solving a problem, no, if you're looking for an approximate solution, so if you want to solve the differential equation, no, approximate solution of the differential equation directly using this weighted residual statement, so you will notice that this is a second order differential equation, because highest derivative in this differential equation of u is second derivative. So whatever approximate solution we assume, it has to be differentiable twice. So the differentiability requirement of approximate solution u is higher. So then what we do is, by using the integration by parts, we transfer the derivative from the variable u to weight function w, and then whatever expression we get, that we call as weak form. So in the weak form, the the differentiability requirement of unknown variable u will be reduced, so it is weakened, and that is why it is known as weak form, because the differentiability requirement of the approximate solution is weaker than the original differential equation, and that is why it is known as weak form. So how do we get the weak form from the weighted residual statement? So as I said, we need to transfer the derivative from u to w, so that is done by using integration by parts. So if we use, say, the integration by parts, so the in the integration by parts, what we do, as I said, that we are going to do only with the first term here. The second term q, of course, we leave as it is. So the first term is integration 0 to L w d by dx of Ea into du by dx. So when we do the integration by parts, so now we are going to transfer the derivative from u to w. So we take w as the first function, and the this d by dx Ea into du by dx as the second function. So when we do the integration by parts, first time we will get w into Ea into du by dx. So this is the boundary term, no, the integration by parts. So we have the first function into integration of the second, and the whole thing is evaluated at the boundaries. So in this case, one boundary is x equal to 0 is one boundary point, and x is equal to L is another boundary point, and then minus integration from 0 to L derivative of first function. So dw by dx, first function is w, so its derivative dw by dx into integration of the second function. So a second function is d by dx of Ea into du by dx, so its integral would be simply Ea into du by dx. So we will get here Ea into du by dx, and the dx, the integration will be there, and then the last term, of course, is integration 0 to L w into q dx is equal to 0. So now if you see, this is a boundary term. After doing the integration by parts, we have two types of terms. One is the boundary term, that is this term, and another is the integral term, which is the integration over length of the domain. So which is actually this term, and of course we have this integral also, wq dx equal to 0. So now if you look at this, so now in the integral term, this particular term, if you see now the highest order derivative of u is only first derivative. So the differentiability requirement of approximate solution is reduced, that now it should be differentiable only once. And of course now we have the derivative of weight function w. So for the first derivative of weight function w, first derivative unknown variable u is also first. There is first derivative of u, unknown variable u. So usually we do the integration by parts such a way that we try to distribute the derivatives equally between the weight function and the unknown variable u, or whatever is the unknown variable of a given problem. So we stop this integration by parts over here. Now since we have the same derivative of weight function w and the same derivative of unknown variable u, so we stop here, and whatever we get we call it as weak form. So this is actually this statement is known as weak form. Why it is known as weak form? Because differentiability requirement of the unknown variable u has reduced, weakened. So as per the differential equation, u should be differentiable twice, but as for this, now it should be differentiable only once, and that is why it is known as weak form. And from the weak form we identify certain things. So when we talk of finite element formulation, so we need to know the information about primary and secondary variables, and also when we want to specify the boundary condition, we need to know about the information about the primary and secondary variables. So we define what are known as primary variables. So in this problem there is only one, so I will just write it as primary variable. So these primary and secondary variables we identify by looking at the boundary term. So in this case, this is the boundary term. Hello, am I audible?
Yes, sir, you are audible.
Okay. Yeah, so please,
Yes.
if you have any doubts and questions, please stop me. So because if there is interaction in between, so then I know that I'm audible. So there is we identify the primary and secondary variables from the weak form, the boundary term of the weak form. And now if you look at the boundary term, why it is boundary term? Because it is evaluated at x equal to 0 and at x is equal to L. So it is evaluated at boundaries. So that is why it is known as boundary term. Whereas these other two terms are the integration over the entire domain. So those are the integral terms over the entire domain. So boundary term, if you see, there are two types of terms in this. One is the weight function term, and another is this variable u term, so which is ei into du by dx. So primary variables we identify by looking at the weight function term in the boundary term. So weight function, if you look at in this case, is w. So primary variable, if we in place of w, if we just think of u, so whatever we get in place of w, if we write u, and whatever we get, that is a primary variable. So in this case, w in place of w, if we write u, so that is going to be the primary variable. So in this case, the primary variable is u. And see, in the mechanics problems, solid mechanics problems, the primary variables are actually geometric quantities. So in this case, u is the displacement, which is a geometric quantity. If we were looking at the fourth order differential equation, say the governing differential equation for Euler-Bernoulli beam, so in that case you will find that the primary variables would be deflection and slope. So both of them are geometric quantities there. So I will take, of course, that as an example. For the timing, we have primary variable as u, and how do we get that? We get it by writing w is equal to u. So in the weight function, we write in the boundary term in place of w, we write u, whatever we get is a primary variable. So in this case, u is a primary variable. And then the other term, which is multiplied to the weight function, is actually secondary variable. And secondary variables are actually force quantities. So in this case, no, there is only one primary secondary variable, which is EA into du by dx. So directly, whatever this term we have over here, that becomes the secondary variable, which is a force quantity. See, because du by dx is strain multiplied by Young's modulus C is the stress, sigma xx, and multiplied by the cross sectional area, it gives you the force. So actually it is axial force. So secondary variable is nothing but axial force, EA into du by dx. So primary variable is a displacement, which is a geometric quantity. Secondary variable is a force, which is a force quantity. So this is one important thing we do from the big form, that is we identify the primary and secondary variables. Then when we also have the classification of boundary conditions.
Sir,
Yeah,
uh, sir, so suppose if in the equation we had dw by dx in the boundary
yeah,
term,
yeah,
then will our primary variable become du by dx?
yeah, it will become du by dx, yes.
Okay, sir.
So now the boundary conditions, so once we identify the primary and secondary variables, so we can also classify the boundary conditions. So the boundary conditions are of two types. For a given problem, the boundary conditions are of two types. One is known as the essential or geometric boundary conditions. In the solid mechanics problems, we also name them as geometric. So essential or geometric boundary conditions. In this case, now for the given problem, if you look at u equal to 0, because we are specifying u at x equal to 0, so that is actually essential or geometric boundary condition. So the essential boundary conditions are nothing but specification of primary variables at at the boundaries. Yeah. So essential geometric boundary conditions are nothing but specification of primary variables at the boundaries. Now, for the given problem, if you look at if you look at as it is this problem, so we have one boundary condition at x equal to 0, where we
Sir,
are specifying the primary variable. Yeah,
sir, if we have dw by dx as primary variable, then
yeah,
u will also primary variable.
yeah. If we have dw by dx in the boundary term, then du by dx will be primary variable. Yes. So you
U
see.
u will be
Primary
also primary.
variable is, yeah, you now see, I will take that kind of an example. So that will happen if you have, let's say, a fourth order differential equation. So in that, when you are arriving at weak form, you will get two boundary terms. So in one boundary term you will have w in that expression, and another boundary term you will have dw by dx. So you will find
Okay,
that there u will be primary variable, and also du by dx will also be primary variable.
okay.
Yeah. So I will take that an example. So I was talking about this essential boundary conditions. So these are the specifications of primary variables at the boundaries. And if you look at for the given problem, so we have at x equal to 0, we have u equal to 0. U is a primary variable, so this is nothing but essential or geometric boundary condition. And the other types of boundary condition is natural or force boundary condition. Natural or force boundary conditions. So these are nothing but what are the natural or force boundary conditions. These are the specification of secondary variables at the boundaries. Secondary variables at the boundaries. Yeah, so now for the given problem, when you look at again, I said there are two boundaries in this. One is at x equal to 0, this boundary, another is at x is equal to L. So because at x is equal to L, the rod is free. No, there is no force along the axial direction. So we have this A into du by dx, and this is a secondary variable, and it is specified at the boundary x is equal to L. So therefore, that boundary condition is a natural or force boundary condition. So we have, as an example, as I said, at x is equal to L, we have this EA into du by dx is equal to 0. So this is an example of the natural boundary condition which is specified at x equal to L. Now, when you talk of the boundary conditions,
Hello,
so
sir.
at a given boundary, yeah,
Sir, how EA into du by dx is equal to 0 at x is equal to L, but we are applying uniformly distributed load, no?
yeah, we are applying the uniformly distributed load, but if you look at the rod, no, so this is the distributed load. This end, this end, if you look at here, this is free. At this end, there is no force. That is how EA into du by dx is equal to 0.
Sir, at x is
Right
equal to
at
L,
this.
force will be Q into L, no?
No, it
At
will
x
not
is
be
equal to,
Q. No, that will be at x is equal to 0. At x equal to 0, the force is going to be Q into L, and at x is equal to L, the force is 0.
okay, sir. Okay.
Because now if you take a free body diagram, take a cut section. So right, you are taking the cut section over here. This side is free, and this side if you take some force, but this length is 0, so the distributed total force due to distributed force is going to be 0. So therefore this is 0. So you can say that at x equal to 0, the net force over here is actually 0, and at x equal to 0, you will have force will be equal to q into L. So if you draw the free body diagram of this, so it would be like this. So this is a distributed force q, and here you will have the force like q into L.
Okay,
So this will be the free body diagram. So here this force is 0. That is how we are saying this EA into du by dx is equal to 0.
okay.
Yeah, so from the big form, as you see, we are able to identify primary and secondary variables. Then we are also able to classify the boundary conditions either as essential boundary conditions or natural boundary conditions. You will see another thing, that at a particular boundary, either primary or the corresponding secondary variables will be specified. Both cannot be specified. So for example, if you look at x equal to 0, so at x equal to 0, you have now the primary variable u equal to, u is specified, u equal to 0. So you cannot specify, no, you cannot fix the no, the secondary variable, that is EA into du by dx. You cannot specify that. Similarly, at the boundary x is equal to L, you can specify only one thing, that is in this case secondary variable EA into du by dx is specified equal to 0, and the u itself, the primary variable u at x equal to L, will be an unknown. We cannot specify that a priori. So at a particular boundary, either the primary or the corresponding secondary variable can be specified. Both cannot be specified. Primary and corresponding secondary variables both cannot be specified at a boundary. So that's another inference we draw from weak form. So and now another thing is from the weak form, we also do one more thing, is that we can find out the corresponding integral functional if it exists for a given problem. So we know, so I'm going to discuss from the differential equation, then we have weighted residual statement, then we have weak form, and then from weak form, how do we get integral functional? So that's the next thing I'm going to discuss. So integral functional, and in solid mechanics problems, we call that as basically the total potential energy functional. So now to do this, we need some interpretation of the weight function. So the weight function W actually is nothing but first variation of the unknown variable U. So to arrive at the integral functional, we take the weight function W as the first variation in U. So now I'm introducing another terminology, that is variation. So in the to arrive at the weight integral functional, we take the weight function. Just a minute, sir. I'm taking class. So yeah, just yeah. So, yes. So yeah, sorry for the disturbance in between. So now I'm talking about the integral functional. So I said that the weight function W is taken as delta U. And what is this delta? This is actually a variation symbol. Variation. So yeah, that means we are taking here W as delta U. So now this variation, I'm going to define what it is. What do we mean by variation? But before that, let me tell you that if we have a single differential equation, then we will have W equal to delta U. But if we have no problem involves more than one unknown variable, then you will have more than one differential equation. So then know the this weight function W in each differential equation will be a corresponding geometric quantity. So for example, here the geometric quantity is U, that is displacement, so its variation delta U is taken as the weight function. If we were having another problem which is involving the axial deformation and also the bending of the same rod, so then you will have the one variable is the displacement along x direction, another would be the displacement deflection along y direction. So you will have one weight function W would be delta U, which would be used in the governing differential equation corresponding to equilibrium of axial forces, and another weight function you will have W equal to delta V, which will go with the the differential equation involved coming from the moment bending moment balance. So for the time being, we have only one differential equation, so the weight function W is taken as delta U. And what is this variation in U? That is variation in U, we are calling it as actually delta U. So what it is? So this is a virtual displacement. So this is not the real displacement, but it is a mathematical concept. So it is a virtual displacement, and it should be kinematically admissible. So I will explain you what is the meaning of that. Kinematically admissible and infinitesimally small. So these are the three things. Infinitesimally, let me write it next line. Infinitesimally small. So what we are doing here, that now if you look at plot of U along the x direction. So for the given problem, if you look at x equal to 0, of course U is 0. So let us say we have some exact solution of the problem. So we are able to solve this differential equation exactly, and we get the exact solution. So let us say this is the exact solution. So this point is x equal to 0, and this is your x equal to 0. Let us say this is the exact solution. Of course, when we want to find out the approximate analytical solution, we don't know this, but let us say that we have an exact solution of the problem. then what we do is we take a virtual displacement which we denote it as delta u. So that is kinematically admissible. So kinematically admissible means wherever the primary variable is specified, so then the variation in the corresponding primary variable there must be 0. So for the given problem, the example I took, this rod problem, u is 0 at x equal to 0. So there u is a primary variable which is specified. So there the variation in u must be 0. So the variation then would be something like this. It is going to be function of x. The variation in u, as you know, weight function w is a function of x, and also the variation in u, that is delta u, is also a function of x. So at let us say we will have the weight, no, the variation in u is 0 at x equal to 0, and then it can have some variation because at x is equal to L, u is not specified, so the variation in u can be any non-zero value as you see here. So this is your plot of u, and this is plot of your delta u, the variation in u. So kinematically admissible means wherever the variable is specified, the corresponding variable, primary variable is specified, there the variation in that variable must be 0. So that is the meaning of kinematically admissible. Virtual, I already told you that it is not a real displacement, actual displacement, but it is a mathematical concept. We call it as a virtual displacement. And the third thing is that it is infinitesimally small. So this is a small quantity compared to u. This is very small. So if you look at the u plus delta u, that is varied displacement would be something like this. So this will be the plot of u plus delta u. So this is what we call this as the varied displacement u plus delta u. So we have a concept of our variation in u, that is delta u, which is a virtual displacement. This is a mathematical concept. This is not a real displacement. It should be kinematically admissible. That means wherever the primary variable is specified, there the variation in that variable must be 0, and it is infinitesimally small. Yeah, any question?
Yes, sir. This delta u, can it be 0 at any other places? Like here?
We are ensuring that at the boundaries where primary variable is specified, there it should be 0, and at other location it could be 0 or it could be non-zero in between. So for example, I have drawn here where you see that at one location delta u is 0. So
Yes,
it can be 0 at intermediate points, but that is not specified. No, we are assuming a function for variation in u, and that function could be 0 in between also. But at the boundaries where primary variables are specified, there the variation in u has to be 0.
Okay, sir. Understood.
Yeah. So now if you look at if I look at, after taking, as I said, to arrive at the integral function, I'll be take w equal to delta u. So now if we look at the weak form after taking w is equal to delta u, so the weak form will be of this delta w equal to delta u. So delta u ea into du by dx at x equal to 0 and L minus integration 0 to L d by dx of delta u, because I am just writing w equal to delta u in the big form, that's all. So ea into du by dx dx, that is the integration, plus integration 0 to L delta u q dx equal to 0. So this will be the big form. Let us do one thing, that let us say the values of secondary variable, that is ea into du by dx at x equal to 0 and L are given by q naught and L. So let us say that ea into du by dx at x equal to 0 is, let us say, q naught, and ea into du by dx at x is equal to L is, let us say, ql. So then we can write this big form as I can say, because this is consisting of two terms. One is x equal to 0, another is at x is equal to L. So I can write it as delta u at L into QL. That is EA.
So
Yeah.
should it
Hello?
be prescribed that x is equals to 0 because we have
Pardon?
essential boundary?
Please say again.
Sir, EA
Sir,
du
should
by
it
dx
be
at x.
prescribed?
Yes.
Sir, EA du by dx, should it be prescribed that x is equals to 0 because we have essential boundary condition there?
If I'm not prescribing, I'm just making using a notation that is E into du by dx at x not at x equal to 0 is q naught. So I am not specifying. I'm just using the notation for
Okay.
EA into du by dx at x equal to 0 as q naught and EA into du by dx at x is equal to L as QL. So I'm just using this notation. That's all. So
Okay.
yeah. So this is the first term know the upper boundary, and minus we will have delta u naught, that is ul is value of u at x is equal to L and u naught is the value of u at x equal to 0 into q naught. So that is going to be the first term, and then we will have minus, of course, that this term. Another thing is, see, we have now, if you look at this particular term, so there are two operators. One is the differential operator d by dx, another is the variational operator delta. So these two are interchangeable. So either you first take the variation of u and then differentiate it with respect to x, or first you differentiate u with respect to x and then take the variation. The two are actually same. So we can also write the second term as delta of du by dx. And then we have this EA into du by dx dx and plus integration 0 to L delta u q dx equal to 0. So no, this is the big form. Now what usually we do, actually, this term, if you look at this integral term, this is going to give rise to what is known as the strain energy of the strain energy stored in the body, and that we want to keep it as positive. So when you get this big form, and if the strain energy density, strain energy is not coming out positive, you multiply the whole expression by -1. So in this case, we multiply the whole expression by -1. That is actually to make sure that the datum for the total potential energy or the integral functional is taken as undeformed configuration of the rod in this case. So in this case, to do that, to take the undeformed configuration as the datum for the integral functional or the total potential energy, we multiply the whole equation by -1. And then now if you do that, so you will get the resulting expression is going to be now q naught into delta u naught minus ql into delta ul, and then plus integration 0 to L delta of du by dx into ea into du by dx dx, and minus we will have integration 0 to L delta u q dx is equal to 0. This is
Hello?
what we
Hello,
will
sir?
have. Yeah,
Hello?
Sir, please, sir,
yeah,
please
yeah.
explain
Tell me.
again this why we are taking minus y potential energy. I can't understand that.
So what I am saying now, if you look at this term,
Yes.
which is minus integration 0 to L delta du by dx CA du by dx dx. So we want to keep this is actually when we do the interpretation of the various terms. So this is the strain energy stored in the body. So this term we want to keep it positive. So finally we want to write the integral functional whose no, because integral functional is total potential energy functional, and total potential energy functional requires a datum. It is written with respect to a certain datum. So to keep the datum as the undeformed configuration of the body, we actually are multiplying this whole thing by a -1. In simple terms, just to keep this term as positive, we are multiplying the whole expression by -1, so that equation is not altered. It is the same equation. Only thing, the relative sign of the terms is changing. So we want to make this term as positive, and this is to make sure that datum for the total potential energy functional is the undeformed configuration of the body.
Okay.
So
Sir,
now, yeah.
sir, that term, is it the variation of total strain energy or
No, is the this term alone is the variation of strain energy, not the total potential energy. It is a
Yes.
okay?
variation of strain energy.
Okay, sir.
Yeah. So now see what we do here. I want to take out this variational operator delta common. So when we take the variational operator delta common, so let me write the delta outside. So here, see, if you look at this, we are treating Q naught and QL no, as the known variables. So we do not take their variation. We are treating Q naught and QL as actually constants. Q naught and QL are taken as constant in the sense of variation. So they are treated as knowns. So the variation of Q naught into U naught would be simply Q naught into delta U naught. So when I take the delta common, I can write that as Q naught into U naught minus QL into UL similarly. And in the second term, because no, the variation is of unknown variable u, so we have delta of du by dx. So when we want to take out delta common from this entire term, so we will have basically half of integration 0 to L, and then we will have ea into du by dx whole square dx. So this is the term we will get. So that means when you take this variational operator delta operate onto this, so this will be half into twice of integral 0 to L ea into du by dx into delta of du by dx. So that would be this term. And then the minus we will have integration 0 to L. When we take delta out, we will get u into q dx, and this whole thing is equal to actually 0. So now in this
Hello, sir.
case, yeah.
Sir, time is running out. 1 minute remaining.
Okay. So yeah, let me increase by 10 minutes. Yeah, so now see what we are doing is we are we are taking this variational operator delta common. So if you take inside this term, the whole term, the first term will give you simply q naught into delta u naught, second term will give you simply minus ql into delta ul, and the third term will give you actually again integral 0 to L delta of du by dx into ea into du by dx dx. So this term, if you look at how we are getting, it is analogous to, if you look at the half of d of x square, that is going to be dx into x. So dx into x is written as half of d of x square. So same way, delta of du by dx into a into du by dx is written as half of a du by dx whole square dx. So this is how you are writing it. So then we say that this is delta into an integral variation of an integral functional I equal to 0. So where this integral functional I is equal to, now let me first write the strain energy terms. So half of integration 0 to L EA into du by dx whole square dx minus integral 0 to L u q dx, and then we have plus q naught into u naught minus ql into ul. So this we call as the integral functional. And now if you look at the various terms in this, so first term is nothing but actually the strain energy stored in the body. So how do we write? So the interpretation of, let us say, I'll call this as the first term, let us call this as the second term, and this together let us call it as third term. So if you look at the first term, which is the first term, that is this one. Now if you look at the strain energy, so strain energy is going to be, let me denote it by pi. So the strain energy pi will be, the half the integration over volume, and the integration over volume can be split into integration over length 0 to L, the integration over cross sectional area A, and then I can write it as half, I have already written over here, and then the strain energy would be half of sigma xx into epsilon xx into dx in dA into dx, the integration over volume. So the integration over volume, I am writing it as dA dx. So then now if you look at this, epsilon xx is du by dx, sigma xx is e into du by dx, and when you integrate over the cross-sectional area, so you get ea into du by dx whole square. So ultimately that is nothing but half of integration 0 to L ea into du by dx whole square dx. So the first term what I have written over here, you see that it is the total strain energy stored in the body, and this we got from the differential equation. See, we started with the differential equation, we are coming to the this expression where we have strain energy stored in the body. And I already explained you, epsilon xx is du by dx, sigma xx is e times epsilon xx, that is sigma xx e times du by dx, and then you integrate over the cross sectional area, you get basically this term. Now if you look at the second term is actually the potential of a distributed load. So if if you talk of this rod, and in the rod there is a distributed force Q, and you take a small element in that, which is of length dx. So in that length dx, the total force would be Q into dx, because Q is force per unit length over a small differential length dx. The total force would be Q into dx. The work done would be into corresponding U at that location. U is a function of x, so that is going to be the work done. And then the differential work done, of course, because due to the differential force over a differential length dx. And then the potential energy is negative of the work done, so minus, and to get the total potential energy of the force, be integrated from 0 to L. So now if you look at the second term, is nothing but this term is the potential of distributed force Q. Potential of distributed force Q. And similarly, if you look at the third term in the integral functional, what I have shown you. So for a general case, of course, finally you have to put the appropriate boundary conditions. But let us say, we have these, the interpretation here is QL. Of course, the given problem QL is actually 0. And here you have Q naught. And the displacement here we are saying as that is a U naught, and the displacement is actually here UL. So if you look at the work done by the force Q naught, it is negative. So the potential is negative of the work done, so the potential will be positive. So the first term potential is work done is minus Q naught into U naught, and then the potential is negative of that, so it will become plus Q naught into U naught. The work done by this force QL will be QL into UL. The work done is positive because the force and displacements are in the same direction. But if you look at the potential, it is negative of the work done, so we will have minus QL into UL. So you will see that this is the potential of forces Q naught and QL. So so this is the interpretation. So if you look at the various terms in the integral functional, this is the strain energy, total strain energy stored in the body. This is the second term is the potential of distributed force Q with datum as the undeformed configuration of the body. And similarly, this is the potential of forces Q naught and QL at the two ends, taking datum as the undeformed configuration of the body. So this is the interpretation of the various terms in the your strain energy, this integral functional. So we also call in solid mechanics problems, I is also called as total potential energy functional. In general, we call it as integral functional, but in solid mechanics problems, we also call it as total potential energy functional. So I think I want to stop here. And if you have any questions, you can ask. We will continue in next class. So
Hello?
is anyone having any question? Yeah, yes, please.
Hello?
Yeah. Yes, please. Yes, tell me, please. Hello. Someone wanted to ask a question.
Sir, I have
Okay, so
one.
if yeah, tell me, please.
Sir, in physical problems, the different human boundary conditions can be taken care of using the concept of essential and natural conditions that you described
Yeah,
in the class.
yeah,
However, in
yeah.
some physical problems, we have Robin boundary conditions, wherein both the derivative of the field variable and the field variable itself are used as boundary. So, how those are handled in finite element framework?
Yeah, then you have to treat both of them as actually unknowns. No, like I have said here, you can have no. You are saying that both of them are specified. You are saying, right?
Uh, Actually, the boundary condition is a function of both, sir. Like in a like
So
fusion
it won't
problem.
be like that. See, the boundary condition has to be either at a given location, either primary variable would be specified or secondary variable would be specified. The boundary condition could be having some non-linearity, so that is possible. That the force might be specified as a some function of unknown no nonlinear function of displacement at that location, or the derivative of displacement at that location. So that may be the situation, but you will never have a case where both primary and secondary variables are specified. You will either specify primary variable or you would specify the secondary variable, not both of them. Primary, corresponding primary and secondary variables, basically. That is what I'm talking.
Sir, like for example, in heat transfer problem,
Yeah,
uh, if the flux at which it is being transferred at the surface is also the
yeah,
function of the temperature of the surface,
yeah.
then it becomes like both the variables are involved.
No, both the variables are not specified, I'm saying. So it would be function of your secondary variable is a function of primary variable, but what is specified is only the secondary variable there. So the temperature will be unknown, and the your heat flux would be function of temperature there. So it has to be taken as function of temperature, and then you solve the problem. Taking the heat flux as the function of temperature. So the procedure would still be the same.
Okay, sir.
From that boundary term also, you will have ultimately, if you look at the coefficient matrix, when we talk of finite element formulation, so stiffness matrix or coefficient matrix. So there, you will have the boundary term will also contribute because it's a function of the primary variable, say temperature. So this will also contribute to kind of stiffness matrix or coefficient matrix. That is what would happen if the secondary variable is specified as a function of is expressed as a function of primary variable.
Okay. Yes, sir.
Yeah.
Sir,
Thank you, sir.
Yeah.
sir, we are considering suppose a simply supported beam. So
Yeah.
one end is hinge. So in that hinge, U is 0 and moment is also 0. So primary and
Yeah.
secondary, sir,
No,
can you?
there's the when you look at the beam problem you are talking about, no, so the primary variables are going to be deflection V and slope dV by dx. Corresponding to deflection V, the secondary variable would be shear force, which would be d by dx of EI into d2 V by dx square. So V will be specified, but the shear force would be an unknown. So secondary variable will be an unknown. The another boundary condition is in terms of the second set of primary and secondary variables. So second boundary condition is that bending moment is 0, but the corresponding primary variable then dV by dx is not specified. That is an unknown at that boundary. So again, you see the same thing, that either the primary variable is specified or corresponding secondary variable is specified.
Okay, sir.
Yeah. So are there any other questions? Anybody? Yeah, I think Krishna Gupta's question in chat box is answered by Devjit. So I already explained you that no, if you have this half of d of x square, which is dx into x, so the half comes from there. When you differentiate x squared, you get 2x dx. So half and 2 gets cancelled. So that is how half is introduced, so that when we take the variation, then that factor 2 which will come from the variation of du by dx whole square, that factor 2 gets cancelled. Are there